All right, let's dive into one of the biggest moments in the history of science. We're going to talk about a single, truly radical idea that completely shattered the physics of the time and kicked off what we now call the quantum age. And believe it or not, this entire revolution didn't start with some huge explosion. It started with a really simple question.
You've definitely seen this before. Think about a blacksmith heating up a piece of iron, or even just the burner on an electric stove. It starts to glow this dull red, right? Then it gets brighter, more orange and yellow. And if you could get it super, super hot, it would turn white hot and eventually even blue. It seems so ordinary, but back in the late 1800s, this was a massive puzzle that some of the smartest people on the planet just could not figure out. See, at the end of the 19th century, physicists were feeling pretty good about themselves. They had Newton's laws of motion, they had Maxwell's equations for light. It really felt like they had a complete, beautiful picture of how the universe worked. But there were these little, nagging problems. A few experimental results that just didn't fit. Little cracks in their perfect theory that just wouldn't go away.
There were three big ones. The first was that glowing hot metal we just mentioned, which scientists called black body radiation. The second was this weird thing where shining a light on a piece of metal could actually knock electrons right off of it. That's the photoelectric effect. And third, there were some strange results when they measured how the heat capacity of solids changed with temperature. Now, classical physics, as powerful as it was, had no answers for any of these. Today, we're going to laser focus on that first one, because solving it blew the whole field of physics wide open.
So let's zoom in on this black body mystery. The reason this was so important is that it got to the very heart of how energy and matter talk to each other. To really study it, though, scientists needed to imagine a perfect object to test their ideas on. And they called this perfect object a black body. Now, in real life, a perfect black body doesn't exist. It's a theoretical concept, an ideal. It's an object that would absorb every single bit of light that hits it. It reflects nothing. That's why it would look perfectly black if it were cold. But here's the kicker. Because it's a perfect absorber, it's also a perfect radiator. So when you heat it up, it glows and emits energy perfectly across the whole spectrum. So how on earth do you build one of these in a lab? Well, this is the clever trick they came up with. You take a hollow box, a cavity, and you poke a teensy tiny little hole in it. Any light that happens to go into that hole is just going to bounce around and around on the inside until it gets completely absorbed. It has almost zero chance of bouncing back out. So that little hole, it acts like a near-perfect black body. Then you can heat the whole box up and measure the light that comes streaming out of that hole. And that is perfect black body radiation.
And when they did that measurement, this is the graph they got. Okay, let's break this down because it's super important. Along the bottom, the x-axis, you've got the wavelength of the light. You can just think of this as the color. You've got long wavelength red light on the right and short wavelength blue and ultraviolet on the left. Then the y-axis going up is the intensity, basically how bright the light is at each color. Now see the two curves? Those are for two different temperatures, where T2 is hotter than T1. And notice how the peak of the glow shifts to the left, to shorter, bluer wavelengths as things get hotter? That's exactly what we see with the glowing piece of metal.
And here is the crisis. This is where everything fell apart for classical physics. The existing theories, all the beautiful, trusted equations, predicted that as the wavelength of light got shorter and shorter, the intensity should just keep going up and up and up, rocketing off to infinity. It was so bad they called it the ultraviolet catastrophe. But just look at the graph of the real data. That's not what happens at all. The intensity hits a peak, and then it drops back down to zero for the really short wavelengths. The theory was totally, spectacularly wrong. Physics was broken.
Enter our hero, a physicist named Max Planck. In the year 1900, Planck was tearing his hair out over this problem. So he decided to just try something, well, something nuts. He himself later called it an act of mathematical desperation. He came up with a solution that he barely even believed, but it had one amazing thing going for it. It actually worked. It perfectly matched the data.
This right here, this was the revolution. Planck basically said, what if we've been thinking about energy all wrong? What if energy isn't some smooth, continuous river? Instead, he proposed that energy can only be given off or absorbed in little, distinct packets, little chunks. He called the smallest possible chunk of energy a quantum.
And this is the absolute best way to picture it. The old classical view was that energy is like a smooth ramp. You can stop at any point along the ramp. You can have any amount of energy you want. But Planck's new idea said no. Energy is like a staircase. You can be on step 1 or you can be on step 2, but you can never, ever be floating in between the steps. Energy only comes in these specific, discrete amounts.
This one simple, kind of bizarre idea had huge consequences. And the best part is, he could capture the whole thing in one of the most famous and important equations in the history of science.
E equals h nu. That's it. This tiny little equation is the foundation stone of all of quantum mechanics. It looks so simple, but what it says about the universe is just staggering.
So let's break it down real quick. E is the energy of one of those little packets, a single quantum. The nu, that's the Greek letter nu, is the frequency of the light, which basically tells you its color. And then there's h. H is the magic ingredient. It's a brand new fundamental number of the universe, and we call it Planck's constant. It's what sets the size of the steps on that energy staircase.
Now here's the crucial thing about h. Look at its value. It is unbelievably, ridiculously small. That's a decimal point followed by 33 zeros and then a 6. Because this number is so tiny, the individual energy steps are so small that we can't see them in our big everyday world. To us, the staircase just looks like a smooth ramp. But if you zoom way, way down to the level of atoms, it's all steps.
So let's just plug in some numbers and see how this works. Say we have some green light, and its frequency is about 5.6 times 10 to the 14th cycles per second. To get the energy of one single packet, one quantum, of that green light, we just multiply that frequency by Planck's constant. And what we get is about 3.7 times 10 to the negative 19 joules. I mean, that is a fantastically small amount of energy, which, again, is why we just don't notice this chunkiness in our day-to-day lives.
So with this one simple formula based on that one wild idea, Planck could create an equation that perfectly matched that blackbody curve from the experiments. It worked. His theory fixed the ultraviolet catastrophe because, in his model, to make really high-frequency ultraviolet light, an atom would have to spit out a really big chunk of energy all at once, and that's just a lot harder to do. It explained perfectly why the curve peaked and then dropped off.
So let's recap the big points here. First, the main idea. Energy isn't smooth, it's quantized. It comes in little packets called quanta. Second, the energy of one of those packets is determined by that core formula, E equals h nu. Third, this idea totally solved the blackbody problem that had stumped everyone. And finally, and this is the big one, this was way more than just a clever trick to solve one problem. It was the birth of quantum mechanics, a completely new way of seeing the universe. You see, Planck's idea, which he proposed so reluctantly, opened a complete Pandora's box. A few years later, Einstein used it to explain that photoelectric effect, and others like Niels Bohr started applying it to the structure of the atom itself. It really leaves you with a mind-bending question to chew on. If energy, which we always thought of as this smooth, continuous flow, is actually made of little bits, what else is? What other parts of the world that look smooth and solid to us are actually, at their core, fundamentally chunky?